Good morning, everyone. And again, please feel free to ask questions through the chat. Dominic can always bring those questions to me, or we can address them at the end. But today, I wanted to take you through 3D printing and additive manufacturing in medical. And it's not only the innovations of Stratasys and our competitors, but it is also a treatise on the innovations that so many of our customers have done and pointed the way of how they are driving innovations in medicine, innovations in clinical practice, and broadly adopting this enterprise 3D printing. As we move forward, I'm going to cover 5 topics and leave some time at the end of this for a bit of Q&A. But first, let's take a quick look at Stratasys today. We shape lives by really revolutionizing the way that things are made. And we'll go through a couple of examples, but I think that Stratasys has changed dramatically over the last 3 years. It was started as Stratasys, the inventor of fused deposition modeling, and Objet, one of the inventors of inkjet-based printing, brought those together into a portfolio. We bought MakerBot, the largest line of consumer-grade printers that are also used in massively in education, but also in certain commercial applications. And finally, we also brought in service bureaus to allow either our customers who already own a printer or those that are just beginning to explore 3D printing or maybe exploring alternative printing technologies that they may not currently own to be able to, in essence, upload an STL file, our standard language for printer files, and try out multiple different technologies. And this has really transformed Stratasys. You can see that not only on the right-hand side as we look across 2011 to 2014 in revenue growth, but we focus on leadership in everything that we do. And Dominic was kind enough to lead into this with where we are in the slope of enlightenment with industrial units. And Stratasys enjoys a 55% market share of the industrial units sold, and we're the largest player in desktop units sold. Mid-year last year, we crossed about 100,000 cumulative systems sold and in service out there. Our printer products range from Idea Series, largely desktop, tabletop units, through the design series, now getting into freestanding inkjet-based and fused deposition modeling printers, and on up to these industrial process. I like to joke sometimes that on the larger sized printers that we have, you could curl up and take a nap in them. Quite sizable, quite high volume production. But perhaps most interesting, and what has unlocked the creativity of our customers, has been a range of material options. Today, Stratasys sells, and through our printers, we can create over 1,200 total material options. This starting from the foundations of the 3D printing industry with stereolithography back in 1986, where there was only one, in essence, brittle plastic. We can now take high-impact plastics, rubber, rigid, high definition, and all the others listed on this slide. So a very broad materials palette, and I'll show you some creative ways in which we use this in the medical field. But first, I like to start this out. I have a 20-year career, anything from a young professor of medicine and engineering at Johns Hopkins, all the way through to founder and CEO of multiple companies. And it always comes down to one question that we need to think about, which is why. And when we look at it, one obvious reason is they are huge markets. These are trillion-dollar marketplaces for products. But perhaps on the second line of this slide, up towards the top, these huge markets have tremendous levels of competition, and they are driven by innovation and market forces. So as we think about that, what matters and what matters to whom? So largely all of you joining us today have participated in some form of healthcare as a patient. And you go see a doctor works at a provider's location. That could be a hospital, a clinic. By and large, you don't directly purchase your medical products. They are provided through a provider. And indeed, throughout the world, throughout the developed world, due to some of the high costs of healthcare, there have risen payers. These can either be the state that are funded through taxes, or in the United States in particular, we have private insurance. When we really look at these four stakeholders in medical, I call them the 4 Ps: payers, producers, providers, and patients. Of course, we are concerned with getting better. Are outcomes good? But it turns out that those same pressures are being forced onto doctors. How many of you have looked up a doctor and taken a look at health grades, or taken a look at ratings of doctors and hospitals? And the other major force beyond outcomes is economics. And we always have to remember these because there are market forces at play. In many countries, the spend that we do on medical is growing faster than the rate of general inflation. We're heading towards 19% of the U.S. gross domestic product will go to healthcare, 1 out of every $5 in our production. Patients have the rise of information access. You can find out a lot about what ails you or what might be affecting one of your loved ones. Payers are now forcing us to look at quality. Up to 20 to 30% of medical spending is wasteful. That's about $800 billion a year. And in the United States, we're now getting to the point where hospitals are going to get their payments cut if they fail on certain performance measures related to the quality of care. And finally, we're still growing as an aging population. By and large, the vast majority of resources are taken in a population dynamic by older members of the population. So all of these are just really pushing us to figure out how do we afford it and how do we drive great outcomes for patients. It's faster and better and cheaper to treat a patient correctly the first time. So as we've looked across our customers, we've come up with 6 key concepts here, and we look at this as the entire medical device value chain. And we'll cover each of these very, very briefly with some great case examples that might spur your creativity in how 3D printing could help you. Starts at the top with rapid prototyping and goes around clockwise in this circle to the point where we get end user medical products, just our terminology for products that would either be worn by a patient, used by a patient, used by a clinician, or even getting to the point of implants. We'll go through each one of those, but again, I want to kind of emphasize that the benefits of this are to accelerate innovations to market, reduced costs in terms of those innovations all the way through to reducing cost and streamlining procedures and improving outcomes. And innovation we'll talk about at the end. Where are we going with 3D printing and additive manufacturing in the future? So now to the heart of this. Let's go around that circle of applications and look at where we started. The roots of our industry started in rapid prototyping. Could you go from a design that you would see on a screen and actually print it out into a physical, tangible object? Millions of years of evolution have given us the synthesis of touch and sight. And indeed, this is where we started. We can accelerate innovation. We can rapidly and iteratively design. In this first example with a diabetes apparatus, we can accelerate the time to verification and validation. This is where it gets so important to understand that today's material options are not just a brittle plastic. We have high impact plastics, high performance aerospace materials that can be 3D printed. And that takes us to the third part here, looking at the arthroscopic surgery device. We can create those functional parts for testing. And medical device design, very often if you are not a practicing clinician, if you're an engineer, you have to bring your products to clinicians for early stage feedback. And that's all part of the bottom part of this, which is communicating ideas. Nothing communicates an idea like a physical model. Today, it is still better than virtual reality. It is better than print on a piece of paper. It's better than my presentation this morning. Seeing, touching is believing much more than just seeing it on a screen. Indeed, in rapid prototyping, if you need to go beyond the materials palette that Stratasys supplies, You can actually leverage the universe of thermoplastic polymers in injection molding, and you can make production grade parts. So we have some examples, and the folks from Tasman could certainly help you with some of our case studies around the ability to make production grade parts. We've done this for small, short production runs to allow companies to get rapidly to clinical trials or to validation and verification. And literally these molds take anywhere from 4 to 24 hours to print out, and the next day you can be shooting parts. It really is highly cost effective and a 90% time savings compared to cutting a metal mold. So going beyond rapid prototyping, that's a great application and still is a tremendous part of our business. We're dedicated to it, we're focused on it, we continue to innovate our printers to allow rapid prototyping. But let's look at some other ways that our customers have harnessed the power of these printers. Before we ever get to a patient, we have to do preclinical testing before we get into the clinic. And one of the opportunities here is to test devices in very realistic anatomical models to accurately simulate clinical performance. So imagine, if you will, that you're trying to design a product to remove a blood clot in the brain of a patient, which we call a stroke. And here we can take the 3D information from a brain scan of a patient and go through this center line of images and create a 3D printed model on the right-hand side that accurately reflects the very real twists, turns, bends, and problems that might have led this patient to have a stroke. Now, when you look on the right-hand side of this image that I'm showing, this 3D printed image, now we can actually put it under X-ray, and we can flow blood through it. So this is not the scan of a brain, this is a scan of a model of the brain. And we can see where that white arrow is. The whole right-hand half of the brain circulation is cut off. This patient is, or this model, I should say, is suffering a stroke. And one way that we try and treat these patients, particularly if they show up at the hospital within the first few hours after the onset of stroke, is to put something called a stent retriever through a tiny little 1 millimeter catheter that we insert up into the brain, and we drag that backwards to try and pull the clot out. And before we've ever tried this product on a patient, we can take a patient's very real anatomy, print it in rubber-like materials that mimic the texture and the toughness of an artery, and we can test the performance. So here we see in the black arrow on the right-hand side image, a portion of the clot has gone further in the circulation. So we could rapidly iterate the design of this stent retriever to try and prevent that exact problem from happening. We can also do the opposite. Aneurysms are little weak areas of an artery in particular, sometimes in a vein, but mostly in arteries, that can rupture. And that is a different type of stroke. And here we want to navigate through this vasculature and put what's called an aneurysm coil, which you can see, this tiny little ball of very, very fine platinum wire that is inserted into the aneurysm and allows it to be walled off by the body so that it will never burst, so we can prevent strokes. So those are just a couple of ideas about preclinical device testing and evaluation. And now as we go further, as we've defined what our products are going to be, we're going to move into the cycle where we're thinking about manufacturing. And as we move to manufacturing, we can rapidly create custom jigs and fixtures. And there are a number of examples. The folks from Tasman can help you with how people are using this on the production floor, but just a couple of examples where educators and research laboratories are utilizing 3D printing to very, very rapidly make jigs, fixtures. These might be for, on the right-hand side, magnetic cell purification, or creating customized pressure gauges using very real materials in our polyjet technology. So these are, again, examples of thermoplastics and FDM and our UV-cured inkjet in the polyjet system. So very, very rapid from concept to deployment, typically in one day. If one of your research students drops a jig, you print it out and you have it the next day. You don't have to order it. You don't have to get it custom fabricated. In essence, you have a digital inventory. And we'll talk about at the end here some of our biocompatible materials that are very useful for creating these highly customized. And when you think about it, it's like, I really want this jig or this fixture to have these qualities, and nobody makes it that way. Now you can in your own laboratory. As we move further around, now we've gone from validating and verifying that the product that we want to make has the greatest potential we can give it to work, where we've moved into manufacturing or customization. Now we go into clinical training and sales aids. To any of you who are involved in medical research, we use a lot of cadavers and animal models and mannequins to train not only the next generation of clinicians, but also to do continuing medical education. All of those have challenges, and the particular one in animals and cadavers is realism and expressing the disease state that we want to treat, but they also have to be in very controlled environments. 3D models can give us the realism, the flexibility, and enhancements over that to be able to cover a full range of clinical requirements and train physicians. So a lot of words on this screen. In my world, a video is worth a million words. So let's take a look at how we might train the next generation of neurosurgeons. And we want to get deep within the brain through the most minimally invasive way possible. And if you're familiar with the brain, which not all of you will be, but there are open spaces, they're called ventricles in the brain, and you can actually pass an endoscope or a viewing telescope deep down into the brain by choosing how to do that with the help of image-guided surgery. So what is unique is this entire head has been 3D printed, and because Stratasys makes the most capable range of multi-material, multicolor simultaneous printers called our Connex 3 PolyJet technology, we can make material that feels like skin. Indeed, you can open it up like skin, and I promise, no real blood within this video. We can also make bone simulation material so that the saw that we use to access the brain actually stops before it goes in. I'm going to advance a little further in the interests of time, and now we're inserting the telescope. We can actually visualize how we're going to take the telescope down into the brain with a computer navigation system. And importantly, remember, we can do multiple textures and multiple colors simultaneously. So as we move deep into the brain, we can actually take a look at blue veins, red arteries, and the open lateral ventricle. As we want to go deeper into the brain, we can actually interact with these digitally printed materials to be able to move further down into the brain, to actually use forceps to cut through this rubber-like simulation of the interior of the brain. And finally, what do we want to teach a neurosurgeon of tomorrow? Sometimes a tumor has a lot of blood vessels growing into it. What do you do if you break open one of those blood vessels and get a bleeder in the brain, what is called a hemorrhage? Well, what ends up happening is very, very simple. Now, obviously, if I was an untrained neurosurgeon, very, very young resident or fellow, I'd be in a panic the moment that I watch my visual field get completely covered with blood flowing through one of our printed blood vessels. But indeed, we can just teach the residents, fellows, that clearing and control of the hemorrhage is just done by irrigation. We have an irrigation bottle that we just apply hydraulic pressure in the brain. It closes the blood vessel, allows it to clot over and heal, and we clear our visual field and continue on with our surgery. So great simulation of reality, and it goes even beyond neurosurgery. I got a chance several weeks ago to be in France teaching an innovation that really came to us from Australia, cochlear implants, and training the next generation of ear, nose, and throat surgeons on a 3D printed model, which you can imagine the cleanliness and the clarity of the 3D printed model is very different from on the lower left. You see what we typically get in ear, nose, and throat surgery and otology trying to do cadavers use cadaver tissue to insert a cochlear implant into the inner ear. Not really representative of what a live case looks like. However, we can 3D print the models to look almost exactly like it. Finally, we can also print out very, very realistic and complicated geometries that anatomically accurate real patient data is used. Salespeople and marketing people can carry this into clinicians' offices to demonstrate devices. They are made without tooling. They're very effective for low volume production. And you can design it once, store it digitally, and print it in Australia, print it in New Zealand, print it anywhere on the rest of the world through the simple transfer of a digital file to the appropriate printer. So now we've trained physicians, we've designed our device. Where else are we going? It is going into personalized procedure kits and the utilization of models. So far I've talked about the utilization of 3D printed models from real anatomical information to design a device, or to prove it out, or to teach a physician how to use it. Well, a great application that is being pioneered in research in university-affiliated hospitals around the world. And I was recently in Australia at Monash University and several hospitals where this is being done today, which is how do we pre-plan? How do we act like an athlete, whether it is a star cricket player or star rugby player? How do you practice as a surgeon? Well, here's an example. Let's take a very real case. This was from the New York Times back in February, and a local group that I've worked quite closely with, Boston Children's Hospital. 2 twins born, the baby girl on the left, Violet, you can see that her eyes are very, very far displaced. And if you're familiar with kids that have a cleft palate, this is a cleft palate that goes all the way up into the forehead. Now, I won't be able to play the video through the link that we have today, but this is Dr. John Mira at Boston Children's Hospital, and he has, he's trying to look inside Violet without doing too much X-rays, too many X-rays, too many MRIs. And indeed what they did was a CT scan of the bony structure of Violet's face. And that gives them information on a screen. We can see that she has this huge defect. But importantly, we're able to take that information very rapidly to the 3D printer that is at Boston Children's Hospital. And there's that image replicated in 3 dimensions. Now here's where we go beyond what you can do with a visualization. We can actually take that, and you can imagine this is going to be complicated surgery. We want to take apart the area of her bony structure around the eyes and put it back together like a very complicated jigsaw. So they printed a number of models, and you'll watch as Dr. Mir brings the parts back together that they cut them very specifically, so they close the gaps, close the holes in her forehead, bring her eyes closer together, and close that Tessier cleft. Now, it's not only that the pre-practice was valuable to the surgeons, but again, when they were in the operating room, they're able to look at the model and think about their approach. Now, what is the problem in the operating room? You don't have X-ray vision. We're not Superman or Superwoman with X-ray vision, so the ability to look at the model and understand what is happening in 3 dimensions is powerful. So you can imagine your precious baby girl is going through some very, very complicated surgery, so it was very powerful to communicate to the parents what was going to happen. And the fantastic news is that they were able to completely rebuild her face to give her a very normal appearance. She'll have some soft tissue repair, but this is happening time and again in very, very complex surgeries. And what is happening is the more physicians get used to this, to practice, to prepare, to make sure that they get those pressures of great outcomes within good economics. This surgery was planned to be up to 18 hours long. They did the surgery in just a little over 10 hours. And when you look at a hospital in Australia, typical rates are about $100 a minute in an operating room. If you can save 8 hours in surgery, it's not only safer for the patient, better for a child from anesthesia times, but it is a real money saver, and the few $1,000s that they spent on models was very, very valuable. And where we see this is not only procedural planning, but it's also now taking that anatomical information and making products. So shaping implants, 2 examples on the right. We can make an orbital implant. So the orbit is the bones around the eye socket. If that is destroyed by cancer, infection, or trauma, accidents, we can reconstruct that with titanium mesh. And here's just a simple way to 3D print a mold to be able to make that mesh so that the doctor did not have to spend 20 or 30 minutes with their fingers and forceps and pliers and the like in the sterile operating room shaping it. And we also see that down in the lower right, where you want to plan out how to repair an aneurysm in the aorta, the main blood vessel coming out of the heart. And they were able to shape the implants and be able to shape the vascular grafts that they use to repair that aneurysm and sterilize them before they got into the operating room. Very short and simple in the bottom, shortened procedure time, improving outcomes are 2 pressures in the medical industry. So finally, where are we heading? Again, just throughout the value chain, let's talk about products that you or I might someday need. And it starts with additively manufacturing. And one great example are low volume production, ideal for clinical trials, pilot commercial launches. These could be of wearable systems in the upper right. It's also to move quickly from a prototype to a final manufactured product. And these are actually being built in the real materials that you would use if you're doing injection molding. It could be ABS, polycarbonate, Ultem. We can also do it on a series of polyjet materials that we'll talk about in a moment. Now, let's take something very prosaic. It's insoles for shoes. These could either be for athletes or it could be for people that might have a diabetic ulcer, might have a lack of bony arch support, they are in pain. Your feet are very, very important to your overall health. We've gone to totally additively manufactured visions of orthotics. Light, airy, super strong, totally customized to the shape of your foot from a scan of your foot. What we also see is a whole new class of prosthetics coming, and here's Limitless, a customer and also a bit of a group that we support. They bring together university students to design unique prostheses for kids who have lost a limb or were born without a limb, and they call it Limitless. And in the upper left, Blue Man Group customized FDM 3D printed prosthetic, another prosthesis in the upper right from a Brazilian soccer star. Down in the lower right, Tony Stark himself, Robert Downey Jr. giving Alex Pring his Iron Man prosthesis, and then a young girl in the lower left with Winter Dolphin, who was discovered injured and has a prosthetic tail and is an inspiration to many, many children and adults with facing disabilities. These are just great examples, highly personalized. As you can imagine in the lower right, Alex Pring went from having a prosthetic to having an Iron Man hand at the age of 7. Pretty cool stuff. So how is this happening in Stratasys' technology? As we look across the solutions, and again, follow up from this, Tasman can help you understand our technologies, but let me just give you a little bit of a flavor of the technologies that Stratasys creates and is constantly innovating on. We have printers that can do single materials, multicolor in the middle, so now we can go to differentiated geometry, digital color coding, all the way through to in the right-hand side, the only current multi-material, multicolor simultaneous prints that allow us to do touch and feel models, dissectable models, digital materials, digital color coding. Really amazing printers. Now, the 2 types of technology, fused deposition modeling. If you ask Scott Crump, the founder of Stratasys and the inventor of this technology, his inspiration was a hot melt glue gun from a crafts project with his daughter, I thought, boy, if I can do that with just a hot melt glue, can I do that with a thermoplastic? And importantly, these are filaments of real thermoplastic materials. There's no chemical reaction. It is just that the material becomes pliable and fusible when you heat it above a certain temperature. And some examples of biocompatible materials that are being used today by our medical customers. ABS, acrylonitrile butadiene styrene. This is a very, very basic material in medical and dental and food and pharma packaging. It is a very, very tough plastic. It is ISO 10993 and USP Class 6. So the materials qualifications are in hand. It is sterilizable by low temperature methods. The same goes for polycarbonate, think bulletproof glass. This is a very, very strong material, and then ultimately we get to Ultem 1010, which is the strongest and highest temperature biocompatible material we make. It has food contact certification, and importantly, what we've learned from our customers for prosthetics and orthotics is that they have to follow the same flame rating. So Ultem we originally developed to make air ducts and support systems that are in aircraft. If you look up Stratasys and airplanes, you'll see that we ship parts every day to go into Boeing 977 and 987, whatever their number is, and the Airbus A350. So you know, this was originally designed for that, and very powerful capabilities for medical devices. FDM advantage, very simple. It's production grade plastics, high accuracy, very stable materials. Reliable and repeatable within the build envelope of our industrial printers, very low cost of operation, ease of use. These can literally be in the office environment, very, very facility friendly, no modifications to a facility needed to put in production. Polyjet is a different material. On the upper left, it's just that icon of inkjet. So as opposed to your home or office inkjet printer, we print a plastic that interacts with UV light to cure from a liquid to a hard plastic. And we have made a number of medical materials. These have been driven by dental applications, dental workups. We have prolonged skin contact up to 30 days and hearing aid materials that are cleared for long-term skin contact and mucosal membrane contact for up to 24 hours. So here again, the folks from Tasman or the folks from my medical group can help you with applications and utility of these different materials within the Polyjet system. Some major Polyjet advantages: it's that simultaneous multi-texture, multi-color, very high resolution in terms of dots per inch, 16 micron layers if you prefer some metric measures, high accuracy, very, very smooth surfaces that can deliver a smooth and glossy surface. You can make very, very thin-walled products, very high build speeds, and again, very simple ease of use of these have been designed so that there are no special skills and automated wizards to maintain. Again, it fits within an office environment, very scalable from our desktop printers up to our large-scale printers, and a variety of materials that you can print simultaneously. So where are we going? We have a very dynamic industry today. Some of the examples that I've taken you through today are going from scanned pixels to anatomy to printed product. These products could be medical models. Today, companies are 3D printing knee implants. They're 3D printing, including our customers, are printing cutting guides to make surgery more rapid and more precise. And we covered in detail a lot of the medical models and the multiple uses for those across the whole life cycle. Where innovators heading? All those same processes, patient information to anatomy information to the printing specificity. We're going towards tissue scaffolds, organs on a chip, printed organs in the future, but today there are myriad uses of our technologies. Just a quick glimpse of the future. So